let us continue our discussion on push-down automaton. Having seen a couple of examples, now you can see that a push-down automaton consisting of the set of states Q, and it has something called sigma, an input alphabet, then gamma, a stack alphabet, and there is something called start state Q naught, and we also have start symbol called Z naught, and then set of final states F, and there is a transition function that talks about how Q cross sigma union epsilon cross gamma is mapped to Q cross gamma star. So for a finite automaton, it is a 5 tuple. You will not see gamma and Z naught, but for a PDA it is a 7 tuple. So what are they? The first one is the set of states, input alphabet, stack alphabet, start state, start symbol in the stack, the set of final states, and the transition function. The transition function is from Q cross sigma union epsilon, because towards the end we look at if the tape is empty, what action we should perform. Which is why when we define the transition function, we say Q cross sigma union epsilon cross gamma. Gamma may contain Z naught, A, B, X, all that, implies Q cross gamma star. We say gamma star because epsilon is something we need. When we say we want to pop, so we need epsilon over there. So it's a 7 tuple describing the automaton, and very similar to FA, one can have a non-deterministic push down automaton and a deterministic push down automaton. So far the examples that we have seen, all of them are deterministic PDA. So for two reasons, to say that it is a deterministic PDA, if you look at delta of Q comma A comma, so some symbol. So delta of Q comma A comma X, where is A coming from? A belongs to this and X belongs to gamma. And for all of them, for any state Q and for any state, for any symbol A and for any stack symbol from gamma, this mapping is unique. Delta of Q comma A comma X is mapped to a unique entry in Q cross gamma star. Correct? Because this one is mapped to this. This is one. And in addition to that, if delta of Q comma A comma X is defined for some Q, for some A and for some X, then delta of Q comma epsilon comma X is undefined. Correct? The reason is the following. If you look at A can be interpreted as epsilon A or A epsilon. Not just that, you can have any number of epsilon followed by A followed by any number of epsilon. Correct? So if let's assume both are defined, then you have a conflict. You look at A, should I read A or should I see A as epsilon A and take this move? Fine. or maybe after reading q comma a comma x, you may read q comma epsilon comma x. So you get to see that you may take this move, or you may take this move. So non-determinism you get to see at this point in time. For a finite automaton, we say delta of q comma a must be uniquely defined, which means it should go to exactly one state. And we say that delta of q comma epsilon is undefined. Correct? For any state, we say the epsilon transition is not allowed. Now, similar thing is what we are trying to mimic in the context of PDA. You say that entry must be unique, and delta of q comma epsilon comma x must be undefined. Okay, if this is defined, then this should not be. Otherwise, what will happen? You get to see non-determinism. When it reads A, the automaton decides whether it is kind of thinking whether it should take this branch and read A, or whether A should be seen as epsilon A and reads epsilon. Okay, so now there are two possibilities at this point in time. Should I see A as A, or should I see A as epsilon A? So there are two possibilities when you look at the symbol. So that brings kind of uncertainty, and that uncertainty brings non-determinism. Fine. So if this is defined, then this must be undefined. So this is precisely the definition for a deterministic PDA. Fine. So this is on one side, and on the other side, we were discussing case studies WCWR, and when we were discussing this, we said we perform push operation until this point, and this will act as a switch. So this will clearly tell us where exactly W ends, and then we start performing pop at this point in time. Then towards the end, we asked, suppose I look at WWR, I drop C, and now can this model be taken forward to describe or to design automaton for WWR? Fine. And this is deterministic in nature. So this is deterministic push down automaton. So DPDA. Now the question is, can DPDA exist for this? Okay. Now the question is, over here we are able to deterministically decide. We are able to deterministically decide that W ends and then WR starts. This will help us. C is actually helping us to deterministically make a call that W ends here and WR starts here. But how do we make such a call over here? So let's look at some couple of examples. Say ABBA. This part is W and this part is WR. Now the automaton has to decide deterministically that W actually ends here and then WR starts from here. But how will the automaton knows? Because the automaton can only read a symbol and move exactly one cell right, and if required switch the state. And it does not know the length of the input, and it does not know the middle point. So all that is not known. Similarly, if you look at say 6 A's, and how will the automaton decide that this is actually W and this is WR? how will the automaton deterministically decide that W ends here and WR starts from here? Okay, so a deterministic machine cannot decide because the machine can only move exactly one cell right. We do not know the length, we do not know the middle point, all that is not given to us. So what will a natural design look like? So the machine has to take a call at each stage whether am I part of W or WR, and R is W stopping and WR starting. Similarly, when it reads this A, it has to take a call, is this A part of W or WR? And similarly, for each A, it has to take a call whether it is part of W or WR. And let's look at this A. There will be one branch that will take the automaton forward, assuming this A is part of WR. Again, there will be one branch, there will be another branch that still says it is part of A. Leave that branch. There will be one branch that says this is part of WR and take the automaton forward. Again, when it is in that branch, it sees another A. Again, it takes another branch that says it is part of WR. So like that, you will find sequence of moves that will take us to the final state. In the context of non-deterministic finite automaton, how did we define acceptance with respect to non-deterministic mission? We said if there exists at least one sequence of moves starting from Q0 to QF, then you accept. So there exists at least one move, there exists a move from Q0 to QF. There may be other moves that may not take us to QF, but there exists at least one that will take us to the accept state. So with this motivation or framework, let's design a non-deterministic mission for WWR. So there are case studies, for example WWR, for which one has to go for a non-deterministic mission. A deterministic mission is not possible. Okay. Later we will see, can we come up with an equivalent deterministic PDA, just like for finite automaton, we say using subset construction, you can always convert NFA to a DFA. On the similar line, can we think of an equivalent mission? But this picture, the way we looked at this example and this example, it kind of intuitively this is giving a picture that deterministic mission may not be possible. Because this picture is telling us length is unknown, middle point is not known, then how will I find the W stops and then WR starts? It's an intuitive picture, and that is kind of telling us a deterministic mission is not possible. Let's see and then try formalizing this picture. Here is the description for WWR. So very similar to WCWR, let's scan and start accepting things. So Q0, comma, A, comma, Z0, and W is a string over A, comma, B star. In this, sigma is AB. There is no other symbol. Now when we see this, now we say Q0, comma, A, Z0. So for this A, we push a symbol, say we say capital A, or gamma contains capital A, and for B it is this. Now Q0, comma, A, comma, we read some more A's, that also we push. So the top symbol is A, We are currently reading a symbol A. For this symbol we push one capital A. So stack the top two symbols are A and A. Now we may read a B. So Q naught comma B comma Z naught. This also we push. Or we may read couple of more B's. That also we push. Fine. Now let's assume with this we are done with W part. Now the question is, what if we read A and top symbol is B? What if we read B and top symbol is A? Okay. So delta of Q naught comma I read A and top symbol is B. Okay. And delta of Q naught comma I read a B and top symbol is A. Okay. So look at this example, AB BA. Now this is our W and this is our WR. Now I read A and I push capital A. Now I am reading a B and what is on the stack is capital A. So now what is that I should do? If you are part of W, then it is push, correct? So which means assuming we are proceeding on the push direction, so this becomes Q naught comma BA. For this B I push capital B. On the similar line, Q naught comma I push capital A on this. Okay, so far we are doing things assuming things work in a deterministic way. But at this point in time, I should take a call. For example, when I read this, now Q naught comma B comma top symbol is B. This says you push B. For this, one direction indicates push, but we want to actually pop, correct? So how will we take that call? So when you are reading this B, I have to take a call that I should switch. Okay, and I should switch and then start performing pop operation. Correct? On the similar line, look at BA AB. Then when you look at BA AB, at this point in time, one branch will tell you push, but other branch should tell us start performing pop. So how will we bring that? And now that will naturally bring non-determinism. Fine. Now you see that this and this are matching, this and this are matching. Similarly, this and this are matching, this and this are matching. So at this point in time, Q naught comma B, one direction says push and another direction should say pop. Go to a different state and perform pop. For this example, one direction should say push, another one should say pop. So again Q1 comma epsilon. Now the moment you go to Q1, you should associate this B with this B. So which means delta of Q1 comma B, top symbol is B, or delta of Q1 comma A, top symbol is A. For both, one has to perform pop. So thinking that we will be performing pop, we start defining transitions with respect to that. Now it is WWR, right? So which means W is a string over this. W can be epsilon as well. Correct? So which means in addition to this, delta of Q naught comma epsilon, start symbol itself is epsilon, and Z naught. With that we go to Q1 comma say Z naught. Okay. Now we are done with this, and once you are done with this, you will be at Q1. You read nothing. Top symbol is Z naught. You can go to final state and keep Z naught, or you can empty this. Okay. So anything is fine. Now this clearly tells you that at this point in time, one branch looks at push, another branch looks at pop, and then starts scanning the automaton. And we clearly see that once you go to Q1, you may start performing some more pop. You are associating this A with this A, next symbol with this, next symbol with this, and so that is taken care by this. Finally, input is exhausted. Top symbol is Z naught. Reach the final state and stop, or empty the store and stop. So for this and this, you clearly see that it is moving to more than one element in Q cross gamma star. Therefore, this is a non-deterministic PDA.